Okay, so in this class, we're going to talk about electromotive force. Now, although the name is electromotive force, we'll explain a little bit later, it's not actually a force. So, in a circuit, the purpose of a battery is to provide a source of energy, right? So the source of energy, which is what we call voltage, okay, so voltage. Now the battery provides voltage. When you're not connecting the battery to a circuit, and when a battery is actually on its own, just sitting there, there is a potential difference, like a voltage difference between the terminal. Now this voltage is called electromotive force. So electromotive force, or EMF. Another time you will see it called EMF, or as a shortcut, just this Greek symbol right here. Okay. Now, despite the name, the electromotive force is actually the voltage of a battery when it's not connected to anything and not an actual force. The confusion comes many years ago when we thought force and voltage were the same thing. But now we know that a force is a physical attraction or repulsion between two objects, whereas the voltage is the amount of energy carried by the electron, right, which is running around in a circuit. So now, at this point, we know that they're not the same thing. But we still keep this convention from a long time ago, calling the voltage of a battery the electromotive force, hence EMF, or that symbol, Greek symbol, right there. For example, when a car's battery is not being used on its own, it carries 12 volts. So we say the EMF of a car battery is 12 volts. And the EMF for a lithium battery, which is like those AA, AAA battery that you can buy, is those like AA or those AAA batteries that you buy outside. Well, the EMF of that is 1.5 volts. Okay. Now however, that number the manufacturer promised you when you buy it is printed on the package is only true if the battery is not connected to anything, which is kind of useless when you think about it, right? So what is the actual voltage you get out from the battery then? Well, as soon as you connect the battery to a circuit, current will start flowing through it, and the voltage will drop slightly. The voltage that you actually measure on the terminal of the battery when the battery is in a circuit will always be less than what is actually advertised to you. So it will be less than the EMF, always. So for example, if you bought like a 9-volt battery and you connect it to your circuit, you're going to discover that the battery only outputs, instead of 9 volts, maybe 8.7 volts, or maybe even less. Now, this is due to a very easy to understand phenomenon though. Well, battery is made of metals. Therefore, battery has internal resistance. Okay, so battery has internal resistance. Now, the internal resistance of a battery is due to the fact that, well, we have to make the battery out of something, right? And any metal, any material carry a little bit of resistance. So the battery has internal resistance inside. Now, because of the internal resistance, we're going to get some internal voltage drop. So internal voltage drop. So that means before the electron can take the energy from the battery and deliver to a light bulb that you collect to, it actually has to drop some of those energy inside the battery to begin with, because the electron has to get out of the battery first. So in our Pizza Hut, remember, in our pizza analogy, what that means, what happened is the electron pick up, let's say, 9 pizza from Pizza Hut. Before they even get out the door, they eat like a slide. So by the time they get out of the door and start delivering their energy, they only have like 8.9 volts left on them because they ate one slide while they're inside the Pizza Hut, so that they have a full stomach and do their job, right? So the terminal voltage is always less than the EMF. So let's highlight that. The terminal voltage is always less than the EMF. So the terminal voltage is what is actually useful when the battery is connected to something, whereas the EMF is the ideal number that they promise you if the battery is not being used, which is pretty useless. So now let's draw a diagram and then figure out the equation. So the diagram that I want you to draw is a battery, and you connect it to a very small resistor, and that's called the internal resistor. And then on the outside, you can hook it up to anything. So that's like a big battery. So the battery is actually like this. So when we talk about battery, usually we just say, oh, that's a power source. Well, it is a power source plus a little bit of internal resistance. So the power source, so what they promise you is this EMF, which is the ideal voltage, which you will never get. And then you have this internal resistance, small r. So internal resistance is small r, and EMF is what they promise you, the ideal voltage. Now, the rest of the circuit, of course, has resistance too. So let's call that big R. So you have the rest of the circuit with like a big resistance, external resistance R. So in this diagram, okay, then it's really clear that, so let's say the EMF is 9 volts, right? So that's a 9-volt battery. So that when the electron comes out, it has to drop some of that voltage in the internal resistance before it can actually get out and deliver the rest of the energy to the big resistor on the outside. So if you look at the internal resistor, then there's some voltage drop in there. So the internal voltage drop in there is, well, total current, because it's linked to the power source, multiplied by small r. This is Ohm's law with the little r. Not Ohm's law on the voltage of the battery, but Ohm's law on that little r only. So this is the internal voltage drop. Internal voltage drop. Now, so when you measure, so what happened is, you have to be careful. So there's an equation that we can pull from here. So let's say, how do we get that total current? Well, to get that total current, we kind of want to think about this circuit as just a normal, regular, perfect battery with 2 resistors. So when you try to get the total current, you need to use Ohm's law, V equal IR, right? But for I, you want I total, and for R, you want R total. And R total is the rest of the circuit's resistor all add together plus the internal resistance collected in series. Okay, make sure of that. Now on your formula sheet, you don't have this version of Ohm's law. So if you would like to add it to your formula sheet, I will actually be recommending that. So if you add that to your formula sheet, so you say, well, yes, Ohm's law is V equal RR. This equation is essentially Ohm's law, but you have the ideal resistance as your voltage, and I total, and R total. R total is your big R. So how do you get your I total is through this equation. Now, as you know, a battery actually has expiry date, and a battery eventually will die off even though you're not using the battery. A battery die off, so when you buy a battery, you look at the expiry date, it's usually like more than 5 years, right? But it does have expiry date. They will say good until this time on the package of the battery. So it has that expiry date because the metal that they use to build the battery will slowly oxidize because it's in contact with the air. And the internal resistance inside will slowly build up. So as the metal come in contact with the air for a extended period of time, the internal resistance slowly and slowly builds up. Now, when the internal resistance builds up too much, then your battery cannot function anymore. So your battery is dead. So that's why you don't buy a battery and leave it there for like 20 years and expect it to work, right? It just doesn't. The internal resistance will actually build up over time. Okay, so there. Now, let's do an example. So if a 12-volt battery has an internal resistance of 0.2 ohm, so this 12 volts, so now we have to ask ourselves, oh, before we do the example, I forgot, let's actually get the equation done first. Okay, there we go, the equation. So now we have this picture below, right here. So now we can write down the equation. Terminal voltage. That means the voltage that you will measure on the battery's terminal after the internal voltage drop, right? Is going to be EMF, which is what they promise you, minus IR. So this equation is on your formula sheet. Now in this equation, there are 2 voltage in here. So watch out. One voltage is the voltage that you can actually use, and the other voltage is the ideal voltage, which you don't really get to use. So this is the voltage. So this is the useful voltage for the rest of your circuit. And this voltage is the ideal voltage, which doesn't really exist. So, well, I mean, it exists inside the battery, but you can't really use it. So IR, right? IR is the internal voltage drop in this equation. So internal voltage drop. Now, on your formula sheet, you are not going to see this like little subscript of total, and it is actually a good idea to put it back on. So on the formula sheet, it would just say V terminal equal to EMF minus IR. But if you add I total to it, then you remind yourself that it's always going to be the total current going into the internal resistance. Okay, so now we can actually do the example. So this example right here, a 12-volt battery has an internal resistance of 220 ohm. So 12-volt battery, 220 ohm. What is terminal voltage if the current is 3 amp? So this battery, 12-volt, is what they advertise. Is the EMF. So it's not what you actually could get. So there's internal resistance. So that's little r, and that's your I total right here. So we have like most of the items ready, and now we just put it in the terminal voltage equation. So terminal voltage is equal to EMF minus I total R. Straightforward applications. So 12 minus I total, which is 3, small r, 0.22 ohm. And at the end, we get the terminal voltage as 11.34 volts. Okay, so now what does that mean? Compare that to the ideal voltage, which is 12 volt. That means the battery was supposed to give you 12 volt, but because of the internal resistance inside, you only end up getting 11.34 volts. That's useful. If you look back at the diagram that we have before on the left, you see, okay, so the battery gives you 12 volts, but the rest of the circuit, the big R, the resistance on the outside, can only get a voltage drop of 11.34, not 12. The other 0.66 volt is dropped in the internal resistance. Okay, so that's what's happening. Now, this example is for charging. So now we have those rechargeable battery, right, which is quite common. And in a rechargeable battery, the equation of terminal voltage actually change. So for rechargeable battery, EMF, the terminal voltage that lead to charge the battery, is equal to I total R, and there's a plus sign. Okay, so it's EMF plus I total R. So to charge a battery, you need more voltage from the outside. So for example, if you want to charge a 12-volt battery, you will need more than 12 volt of power supply to force the electron to go back in. So this equation is for charging. Okay. So I hope it makes sense, because think about it. So for example, your cell phone has a battery that is approximately 5 volt. So it has a cell phone battery. So you have a cell phone battery that is 5 volts. But in order to charge that battery, which is 5 volts, you will need to provide a terminal voltage that's more than 5 volts to make the electron go backward into the battery. It takes energy to move energy. Remember we say that. So when you charge a battery, you need more energy than what you wanted to actually charge. If your battery is 12 volt, then you need more than 12 volt to charge it up. That's what happened. Okay, so this terminal voltage is the voltage needed to charge the battery. Okay, whereas the EMF is the voltage of the battery that you wanted to charge. Now on the formula sheet, this equation and the last one for using the battery, the other one for charging it, are put together. So you have a plus or minus sign. So you need to make sure you know the plus sign is for charging, the minus sign is for using the battery, for discharging the battery. Okay, so our last example for today. So V terminal. So what we have is a 12-volt car battery, and we want to charge it by an alternator that can supply 15 volts. So 12-volt battery, but we need to supply 15 volts to charge it. So obviously this is V terminal, and this is the EMF, is what you want to charge. And there's internal resistance, and we want to find the current, which is pretty straightforward. So terminal is equal to EMF plus I total R, and it is a plus because we are charging, and we put 12 volts on here. That's what we want to charge up, but we're charging up with 15 volts collected to the battery, and I total R 1.3 ohms. So at the end, if you go through the calculation carefully, then I total works out to be 2.3 amp, and that's it. Okay, so now at this point you have all the weapons for this chapter. So you have Ohm's law, Kirchhoff's law, and this. So there's a worksheet on the back called worksheet 7.4, I believe, and that should be what you're working on for the rest of the class. So if you have any question, I'll be here tomorrow, Thursday. So if you have any question that you need to ask me, you can come find me tomorrow. And so work on the worksheet and have a good day. Thank you.